Our solar system is a place of wonder, a celestial ballet of planets, moons, and stars. In this vast expanse, there exist breathtaking phenomena that captivate the imagination. Amongst these wonders are the planetary rings, shimmering bands of ice and rock that encircle some of our celestial neighbors. These rings, far from being mere decorations, offer a glimpse into the formation and evolution of planetary systems, including our own. They are celestial mysteries waiting to be unraveled. Our journey into the realm of planetary rings begins with Saturn, the jewel of our solar system. Saturn's rings are the most spectacular and easily observed, a sight that has mesmerized astronomers for centuries. But Saturn is not alone in possessing these celestial adornments. Other gas giants like Jupiter, Uranus, and Neptune also boast their own unique ring systems, each with its own story to tell. These rings, despite their ethereal beauty, are not solid structures but rather a collection of countless particles, ranging in size from tiny grains of dust to massive boulders. These particles, trapped in a delicate gravitational dance around their parent planets, paint a breathtaking picture of cosmic harmony. Join us as we embark on a journey to explore these enigmatic rings, delving into their formation, their composition, and the secrets they hold about the universe we call home. Imagine a celestial tapestry woven with threads of ice and rock, shimmering against the backdrop of space. This is the sight that greets us as we venture closer to the ring systems of our solar system. These rings, far from being uniform and static, are dynamic and ever-changing, shaped by the relentless forces of gravity and time. Each ring system tells a unique story, a tale of cosmic collisions, gravitational captures, and the intricate dance between planets and their moons. In the case of Saturn, its majestic rings are believed to have formed from the remnants of shattered moons, comets, or asteroids, torn apart by the planet's powerful gravitational pull. These fragments, once part of larger celestial bodies, now orbit Saturn in a perpetual dance, creating the breathtaking spectacle we observe from afar. Jupiter's rings, fainter and less prominent, are thought to be the result of dust kicked up by meteoroid impacts on its inner moons. Uranus and Neptune, the ice giants of our solar system, also possess ring systems, though theirs are darker and less reflective than Saturn's. These rings are believed to be composed primarily of organic molecules, darkened by exposure to radiation from the distant sun. The study of these diverse ring systems provides valuable insights into the processes that shaped our solar system and continue to shape planetary systems across the cosmos. The exploration of planetary rings is not merely an exercise in aesthetics, but a scientific endeavor of great importance. By studying these celestial structures, we gain a deeper understanding of gravity, orbital mechanics, and the processes that govern the formation and evolution of planetary systems. The rings act as cosmic laboratories, preserving evidence of past events and offering clues about the early solar system. The gaps and divisions within these ring systems are not random, but rather sculpted by the gravitational influence of nearby moons. These moons, known as shepherd moons, play a crucial role in shaping and maintaining the ring structures, their gravitational pull acting as an invisible hand guiding the ring particles. Furthermore, the composition of the ring particles provides valuable information about the building blocks of planets and the conditions that existed during the early solar system. The study of planetary rings also has implications for our understanding of protoplanetary disks, the swirling disks of gas and dust that surround young stars. These disks are believed to be the birthplaces of planets, and the processes that form rings around planets may hold clues to the formation of planets themselves. As we continue to explore and unravel the mysteries of planetary rings, we gain a deeper appreciation for the beauty, complexity, and interconnectedness of our universe. In the vast expanse of space, gravity reigns supreme, shaping the destiny of stars, planets, and all celestial objects. This force lies at the heart of planetary ring formation, dictating the dance of particles around massive bodies. Gravity is a force of attraction between any two objects with mass. The more massive an object, the stronger its gravitational pull. Imagine a celestial ballet with gravity as the choreographer guiding countless particles. These particles, remnants of comets or moons, are drawn into orbit, creating ring systems. Section 2. A Cosmic Demolition Derby. The formation of planetary rings often begins with a cosmic demolition derby, a violent event that shatters celestial bodies into countless fragments. These fragments, once part of larger objects like moons, comets, or asteroids, become the building blocks of the ring systems we marvel at today. Imagine a rogue asteroid straying too close to a giant planet. The planet's immense gravitational pull, like an invisible hand, stretches and squeezes the asteroid, tearing it apart in a spectacular display of cosmic violence. This process, known as tidal disruption, can also befall moons that wander too close to their parent planets. In other instances, high-speed collisions between objects in the early solar system can send showers of debris into orbit around a planet. These collisions, remnants of the chaotic early stages of planetary system formation, provide the raw materials for ring systems to form. Once these fragments are in orbit, the relentless force of gravity takes over. The planet's gravitational pull prevents the fragments from escaping, while collisions between the fragments themselves grind them down into smaller and smaller pieces. Over time, this process of collision and fragmentation shapes the ring system, creating the intricate structures we observe. Section 3. The Roche Limit. In the intricate dance between gravity and celestial bodies, there exists a critical boundary known as the Roche Limit. This invisible line, named after the French astronomer Édouard Roche, marks the point at which a celestial body, held together by its own gravity, will be torn apart by the tidal forces of a larger object. Imagine a moon venturing closer and closer to its parent planet. As it approaches, the planet's gravitational pull becomes stronger on the side of the moon facing the planet compared to the side facing away. This difference in gravitational force, known as tidal force, stretches the moon, creating a bulge on both the near and far sides. As the moon crosses the Roche limit, the tidal forces exceed the moon's own gravitational binding energy. The moon, unable to withstand the relentless pull, is ripped apart, its fragmented remains scattered along its orbital path. These shattered remnants, held in orbit by the planet's gravity, form the basis of a ring system. The Roche limit is not a fixed distance, but rather depends on the masses and densities of the objects involved. For a planet like Saturn, with its massive size and relatively low density, the Roche limit extends far outward, allowing it to capture and shred objects that stray too close. Section 4. Ring systems in the making. The formation of a planetary ring system is not a singular event, but rather an ongoing process, shaped by the interplay of gravity, collisions, and the passage of time. As ring particles orbit their parent planet, they continue to interact with each other, creating a dynamic and ever-changing environment. One of the key processes that shape ring systems is resonance. Just as a vibrating tuning fork can cause another fork to resonate at the same frequency, the gravitational pull of nearby moons can create regions in the ring system where particles experience a stronger gravitational tug. These resonant locations can act as gravitational shepherds, confining particles to specific orbits and creating gaps and divisions within the rings. Collisions between ring particles also play a crucial role in shaping the ring system. These collisions can grind down larger particles into smaller ones, creating a distribution of particle sizes within the rings. In some cases, collisions can even lead to the formation of new moons, as particles clump together under their own gravity. The composition of ring systems also evolves over time. Micrometeoroids, tiny particles of interplanetary dust, constantly bombard the rings, adding new material and altering the ring's chemical makeup. Radiation from the sun and other sources can also alter the composition of ring particles, leading to changes in their color and reflectivity. Amongst the celestial wonders of our solar system, Saturn stands apart, adorned with a crown of breathtaking splendor. its iconic rings. This gas giant, the second largest in our solar system, is a celestial spectacle, a testament to the awe-inspiring forces that shape our universe. Saturn's rings, far from being a mere accessory, are a defining feature, captivating observers for centuries. The first glimpse of Saturn's rings through a telescope is an experience etched in the memory of every sky gazer. The rings, seemingly impossibly thin and perfectly formed, appear as if painted onto the sky. Yet these rings are no illusion but a testament to the intricate dance of gravity and matter. Saturn's rings are composed of countless individual particles, each on its own independent orbit. These particles, ranging in size from tiny grains of dust to massive chunks of ice, create a mesmerizing spectacle. As sunlight reflects off these countless particles, the rings shimmer and sparkle, illuminating the darkness of space. The ring's structure is a complex tapestry of interwoven bands, gaps, and ringlets, sculpted by the gravitational influence of Saturn and its moons. To truly appreciate the grandeur of Saturn's rings, we must journey closer, beyond the limits of our telescopes, to unravel the intricacies of their structure. Imagine a vast disk spanning hundreds of thousands of kilometers, yet remarkably thin, with a thickness averaging a mere tens of meters. The A, B, and C rings are the most prominent, each with unique characteristics. The A ring is separated from the B ring by the Cassini division, named after Giovanni Cassini. The B ring is the brightest and most massive, with particles constantly colliding. The C ring, also known as the crepe ring, is fainter and more diffuse. Beyond these main rings lie the D, E, F, and G rings, extending far outward. These rings are dynamic, with particles constantly colliding and influenced by Saturn's moons, a celestial kaleidoscope of motion and light. The brilliance of Saturn's rings is a testament to their composition. They are made primarily of water ice. These icy particles, remnants of comets, asteroids, or shattered moons, reflect sunlight like countless tiny mirrors, creating the dazzling display we observe from Earth. However, the rings are not solely composed of pristine ice. Interspersed amongst the icy particles are traces of rocky material, remnants of the objects that formed the rings. These rocky fragments, often coated in a thin layer of ice, absorb more sunlight than the icy particles, giving the rings a subtle mottled appearance. The proportion of ice to rock varies throughout the ring system, influencing the ring's brightness and reflectivity. The size of the ring particles also varies dramatically. Some are no larger than grains of dust, while others are massive chunks of ice exceeding the size of houses. These larger particles, often referred to as ring moons, create their own gravitational disturbances within the rings, sculpting gaps and ringlets in their wake. The composition of Saturn's rings provides valuable clues about their origin. The abundance of water ice suggests that the objects that formed the rings were rich in volatiles, suggesting they originated in the outer solar system, where icy bodies are more prevalent. Section 4. Shepherd Moons and Gravitational Choreography. The intricate structure of Saturn's rings is not merely a random arrangement, but a testament to the delicate gravitational interplay between the rings and Saturn's many moons. These moons, some embedded within the rings themselves, play a crucial role in sculpting and maintaining the ring system, their gravitational influence acting as an invisible hand guiding the ring particles. Some moons, known as shepherd moons, orbit within or near the edges of the rings. These moons, through their gravitational pull, act as cosmic shepherds, confining ring particles to specific orbits and preventing them from spreading out. The Cassini division, the prominent gap between the A and B rings, is maintained by the gravitational influence of the moon Mimas. Other moons create wave-like disturbances in the rings, their gravity leaving its signature on the ring structure. These waves, known as density waves and spiral waves, propagate through the rings, altering the local density of ring particles and creating intricate patterns. The gravitational influence of Saturn's moons is not limited to sculpting the rings. Some moons, through a process known as resonance, can clear out gaps within the rings. When a moon's orbital period is a simple fraction of the orbital period of ring particles, the moon's repeated gravitational tugs can nudge the particles out of their orbits, creating a gap in the ring system. Section 5. Beyond the visible spectrum. By observing Saturn's rings at different wavelengths, astronomers have uncovered hidden details and complexities. Infrared observations reveal temperature variations, while ultraviolet observations detect water, ice, and organic molecules. Radio observations provide insights into the structure and dynamics of the rings. Section 1. Beyond the reach of Saturn. Other gas giants like Jupiter, Uranus, and Neptune also possess ring systems. These rings, though fainter, tell unique stories of cosmic collisions and gravitational captures. Each ring system is a testament to the chaotic history of our solar system. Jupiter, the king of planets, reigns supreme in our solar system. Discovered in 1979 by Voyager 1, Jupiter's rings are faint and composed of tiny dust particles. These particles are debris from micrometeoroid impacts on Jupiter's inner moons. The rings are constantly replenished by dust from these moons. Uranus, the ice giant tilted on its side, has a unique ring system. Discovered in 1977, Uranus's rings are dark and narrow, reflecting less than 5% of sunlight. The rings are thought to be remnants of shattered moons or other objects. Shepherd moons play a crucial role in confining the rings. Neptune, the outermost gas giant, has a ring system as enigmatic as the planet itself. Discovered in 1984, Neptune's rings are composed of dust particles. The rings form clumpy arcs, influenced by the gravity of Neptune's inner moon, Galatea. These arcs are dynamic, changing over time. The ring systems of our solar system paint a diverse family portrait. Saturn's rings are the most massive and complex, shaped by gravity over billions of years. Jupiter's rings highlight the role of small moons in generating ring material. Uranus's and Neptune's rings showcase the dynamic nature of planetary systems. Our journey through the solar system's ring systems reveals unique characteristics. Saturn's rings are majestic and sprawling, while Jupiter's are faint and dusty. Uranus's rings are dark and narrow, suggesting a young system. Neptune's rings, with their clumpy arcs, highlight the influence of gravity and resonances. The ring systems of our solar system vary greatly in size and scale. Saturn's rings span hundreds of thousands of kilometers, while Jupiter's are smaller. Uranus's rings are even smaller, and Neptune's are the most compact. The size of the ring particles also varies significantly between the different systems. The composition of planetary rings provides clues about their origin. Saturn's rings are primarily water ice, while Jupiter's are tiny dust particles. Uranus's rings are dark, likely due to organic molecules. Neptune's rings contain a mixture of silicates, ices, and organic molecules. Planetary ring systems are dynamic environments shaped by gravitational forces and collisions. Saturn's rings showcase the power of these forces to sculpt matter over billions of years. Shepherd moons and wave-like disturbances play crucial roles in shaping the rings. The rings of Jupiter, Uranus, and Neptune are also dynamic, constantly evolving. Planetary rings, those ethereal bands of ice and rock, are far more than celestial decorations. They are dynamic structures, shaped by gravity, collisions, and time. Exploring Saturn, Jupiter, Uranus, and Neptune's rings reveals cosmic wonders and the interplay between planets, moons, and rings. Their study provides a window into our solar system's history and planetary systems. Analyzing their composition offers clues about the early solar system. Their dynamics reveal the gravitational dance between planets, moons, and rings. Beyond science, their beauty inspires us to explore the universe. They remind us that beauty can arise from chaos, and the universe is full of wonders. Exploring planetary rings deepens our understanding of the cosmos.